Hey physics fans, and welcome back to your problem on Introduction to Rotation. Today we're going to be looking at text problem 10-39 in your OpenStax textbook. Now after reading this problem, we notice that we have a rotating object with an initial and final angular velocity over some time. So this is a rotational kinematics problem. In part A, it asks for us to solve for the angular acceleration of our rotating object. And in part B, it asks for us to solve for the displacement that object undergoes after speeding up to 1500 revolutions per minute. The physics, well, we have to look at our rotational kinematics equations, and I've identified a few that will help us out in this problem. Additionally, make sure you convert all of our units to revolutions per minute to radians per second before you get going. For our draw step, we have a rotating object. I've given it an arbitrary direction because it didn't give us one to start out with. Therefore, I'm assuming that all of our solved quantities are going to be the magnitudes and not in a direction. For our given quantities that we discussed, we have an initial and final angular velocity of our object, and we have a time that it takes to get from that initial to final angular velocity. We have to assume that it's a constant acceleration or none of our kinematics equations work. Now let's move on to the solve step. In part A, we're asked to solve for the angular acceleration of our object. So we can look at our first kinematics equation, and it gives us all of the variables that we need to solve for the angular acceleration of our rotating object. So we have one equation and one unknown, and we can solve for it comes out to 0.87 radians per second squared. But the least amount of significant figures is 500 revolutions per minute, so we're going to use one significant figure. For part B, it asks us to solve for the displacement of our object through that acceleration. Well, the displacement is the final minus initial angular position of our object, so we have one equation that has all of our givens plus the quantity we solved for in angular acceleration, and what we are solving for in part B, which is the final minus initial angular position. So we can isolate the final minus initial angular position and solve for the displacement of our object, which comes out to about 66,000 radians. But once again, we're going to use one significant figure and round it up to 70,000 radians. For our check, we made sure that our displacement was in radians and our angular acceleration was radians per second squared. We've rounded them both to one significant figure, and both of these answers seem reasonable. Thanks, and we'll see you next time.